All right. So, as Aisha said, I'm Nathan Mathabane, a University of Oregon second-year RESESS intern, and I was working with my master's advisor, Joshua Roaring, at the University of Oregon in Eugene, Oregon, beautiful Eugene, on landslides. And basically, essentially, what we're doing is trying to come up with new and better methodologies for dating landslides, because they fall into this really interesting window where they're a little young to be dated with like traditional radioisotope data like uranium and thorium, but they're too old to be dated by stuff like carbon. So at least the ones that we're going to be looking at, and I'll get into that now. So this is going to be a story about landslides, particularly very, very old landslides. So I just included these slides just to show, get people excited and jazzed up about landslides, because they can be pretty awesome. There's a Taiwanese one on the left, which I thought was the coolest landslide I've ever seen. Coolest being like a relative term here. And one that's more similar to the study area is going to be the one on the right, which is in the Puget Sound, which is in the Pacific Northwest, where my study area is. So I'm going to talk a little bit about the Pacific Northwest and why it's such a cool place to be studying landslides. So I did all of my work in the Oregon Coastal Range, which is the mountain range in between the Willamette Valley and the Pacific Ocean, and it's formed by compression of the Juan de Fuca plate against North America. So Pacific plate coming in, creating this little compressional lip. They're little baby mountains. They're like 1,500 feet tall, so they're not that exciting, but in terms of relief, but they're still pretty cool. So I was working in the Blue Formation, which is called the Tyee. It took me forever to figure out how to pronounce that word. And it is a interbedded sandstone siltstone formation that overtops the Oregon Coastal Range. And that's particularly important because all the landslide failures occur on the siltstone beds along the dip plane. So that's just some useful geology to know about the region. And the Oregon Coastal Range is actually super, super cool for studying geomorphology because, A, it's an active tectonic environment, so you have uplift, so you're getting awesome relief, which is important for looking at landslides. Landslides aren't going to occur in the Great Plains, obviously. And you also have 200-plus days of rain a year, which anyone from the Pacific Northwest knows to be a reality. So you have this awesome kind of cocktail, which is going to lead to a lot of landslides. So landslides have been studied extensively, especially in Oregon, but it's mostly been historical landslides, so landslides happening in the last 200 to 400 years that we have record of, and it's easy to drive down the highway and see an obvious landslide. Oh, there's like a bunch of ripped up trees, just some destroyed houses. It's pretty easy to tell that those are landslides, but the landslides that I'm interested in are really old bedrock landslides that occurred anywhere between 50 and 200,000 years ago. So these are things that you can't just drive your Subaru down the road and see that that's a landslide. In order to actually realize that these are landslides, you need to be used like LiDAR. So this is actually pretty awesome. This is like my favorite slide in the entire presentation because it shows the contrast between aerial photos and LiDAR and why it's so useful for looking at landslides. Because if you look at the aerial photo on the bottom, how many of you would think that that was a landslide? Like, I wouldn't. So when you look at the exact same thing in LiDAR, you can see how bench-like the topography on the slide is compared to the dissected, very regular terrain that you see just across that gully. So that's the kind of dissected terrain that really characterizes the Oregon Coastal Range. So when you have a departure from it, which you can see in LiDAR, you can tell there are these ancient landslides pretty much all over the place, which is really cool, and we couldn't do until like recent developments in the resolution of LiDAR. So thanks for people who do LiDAR, like UNAVCO. So now that we know where these ancient landslides are, it was my job to go and date them and test them and see how old they were, because with the ultimate goal of figuring out, if we get cool clusters of these landslides, what are the tectonic and climatic consequences of that? And were these ancient landslides caused during a big glacial period or something? So we just want to kind of have a clustered time set that we don't have right now because we can't date these things. So what I would do is I'd go troop out to those landslides, and I'd go up and walk around them with my auger and machete and shovel and take little Ziploc baggies of dirt, 4 to 7 per landslide. Hopefully that was on a good day. And then I'd take those back to the lab for analysis. So what we were looking for was we wanted to get all the organic matter out. So we went to the B soil horizon. If you guys know your soil profiles, O, A, B, C. We wanted the B one because that doesn't have any organic matter in it. And organic matter would interfere with VisNear, which is visual near infrared spectroscopy, the type of tool we're going to be using to date these things. So we didn't want any organic matter messing with our stuff. So we had a combination of auger cores and road cuts is where we got our data from, our little samples. And I would take them back to the lab and throw them in the little tins, these cool little tins that I washed. And they'd dry out, and then I'd sieve them down to 63 microns, because that's when you get all the junk out, and you just really have the fine, silty material that's going to be useful for our analysis. And then I put them in these little Petri dishes, and I ran them in this spectrometer. And basically what the spectrometer is looking for is the redness of the soil sample, because the redness is directly correlated with the amount of hematite in the soil sample, and the amount of hematite in the soil sample is directly correlated with the age of the sample. Because as something weathers at the surface over time or near the surface, it accumulates more and more hematite, something that's been proven by my professor and previous professors in the Oregon Coastal Range before. So we have this nice little chrono sequence where you know that more yellowish soils are younger and more reddish soils are older, and we have quantitatively measured that. So by looking at the redness of the soil, I can tell you how old these landslides are. That's the basic methodology. Here's what the spectra look like. So this is the sample. Next to it, spectra. And you can see that right around 880 nanometers, which is the peak for hematite, you can see that there's a little dip, because this is a measure of reflectance, so it's going to be inverted. So you can see a little dip where the hematite is. And that's really nice, because you're like, oh, look, there obviously is hematite in here. It's a red sample. It's going to be pretty old. If you compare this to another younger slide, you can see that that peak is not really a thing. Check it out. Boop, valley, boop. No, it's not there. So this slide is about 80,000 years old. The other one is 220,000 years old. So you can see how that kind of a difference in spectrum emerges. And we did this for all the samples. So we got this nice catalog of 30 different soil samples. And we put them on this nice little chart in ArcGIS. And you can kind of see the distribution of the slide data. So what we were going for was, our hypothesis was that slides would be relatively homogeneous. That's what we'd like to think. You know, if this slide all moved at once, it would all have the same age. Turns out, if you look at the legend and look at the dots, it's not always the case. Especially in the older slides, like Wolf Creek and Vaughan, you can see that there's kind of a lot of heterogeneity in the ages. Especially like the red ones are really big, old outliers that I don't like, but they're there, so we have to deal with them. And there are reasons and theories that I address in my research article, if any of you are interested, as to why I think those occur. Just brief summaries of those. One thing could be differences between auger cuts and soil, road cuts and auger samples. A lot of the oldest samples were taken from road cuts, so there could be some kind of confounding weathering going on at the surface that's messing with the type of spectroscopy that we're going to be doing. You could also often have multiple landslides appearing as a single landslide, but they're actually a complex of landslides that have occurred at multiple times and kind of all slumped together, and that's why you could be getting differences in ages. So there's a lot of reasons. One key conclusion, though, is that the older you get, the more the standard deviation on your slide goes up. So in the younger slides, like Taylor Creek, you can see they're relatively uniform, whereas if you get older, you get more error associated with your slide. So those are some of the bigger conclusions. Just a general histogram of the ages. They tended to be clustered between 75 and 150,000 years in age, these ancient bedrock landslides. But we obviously had outliers going up into the 300,000 year age. The only problem with this type of analysis is that hematite saturates at around 200,000 years of weathering, so it becomes very, very difficult past that point to tell how old the slide is, because at 200,000 years, you're basically at as much hematite per area as you're going to be getting. So the error associated with that goes up, because even slight increases in hematite could occur over tens of thousands of years. So a major takeaway from this presentation is that the soils constituting a landslide complex can be varied in, that's a typo, in and type of weathering, even in a limited area. So I'd like to thank Josh, my boss over at Oregon. He's a really, really awesome guy, and he's been super helpful all along the way. I'd like to thank Karina. She was my grad student, so people hate it when I say my grad student. I don't know how else to say that. I was her grad student. She led me around the field and had me dig auger samples, and it was really cool. And Kristen Sweeney wrote the MATLAB code that we used for the visible near-infrared spectroscopy. UNAVCO, obviously, for sponsoring the RESESS program, and the RESESS program for taking me back for a second year. It's been awesome, and the NSF for funding this entire business. So that is my presentation. If you have any questions about landslides, I would be more than happy to take them at this time.
Hi, Nathan. I really liked how you talked about the possible sources that might have caused the heterogeneity that you got in the dates from landslides. Between the spectroscopy methods themselves, the sampling location between boreholes and road cuts, and the multiple slides on the landslide itself that might cause this heterogeneity, do you have any guess as to which of those is more of a driving factor?
Yes. I think that the biggest source of error is that hematite accumulation. And that is just, that's not data supported, but I've been reading research since having written this paper, and the different pedogenic being soil weathering pathways down which a single parcel of soil will go could mean that some more yellow soils are actually older than they appear because they weather in a different way than we base our model on. So I think it has something to do with the way the soil weathers more than road cuts, more than multiple slides, more than anything else.
Great, thank you.
So were all the landslides happening in one rock formation? And did
all in the Tyee.
Okay, did you know the age of it?
It's mid Eocene. No, not Eocene. Mid Miocene. So that's going to be, it's in my research article. I think it's Miocene. Anyone? Huh? Yeah, like 16 million, I think. So geology, time scales. Yeah, so that's when it was deposited.
Okay. Is it poorly lithified?
Is it poorly lithified?
Yeah.
Yeah.
Okay.
It was deposited when Oregon was quite temperate, actually, like kind of tropical more, which is cool because I didn't know that was a thing.
I actually have a question. Could you comment on how, like, this is a new method that you're testing?
So
like, how long?
Visnear is not new.
Yeah.
But the way that we're using it to date landslides is.
So is this? Can you just comment on the newness of the technique a little bit?
Yeah, absolutely. So the technique was first fleshed out in 2007, at least in Oregon. So what we did is we went and looked at a bunch of terrace sequences along the Siuslaw River. And it's cool because there are these 7 river terraces that are pretty much uniformly distributed. So by collecting soil from each of those and knowing how old those terraces are, you can get a redness amount from those terraces, and we use that to fit a curve and get a model for the age based on redness.
Thank you.
Yep.
Okay, thank you, Nathan. So we're going to have about